In the last lecture, you have seen that we have defined the new function, that is Dirac delta function, and how to find out the Laplace transform of the Dirac delta function. In this lecture, we will go through one more function, that is the Bessel function. If you see, Bessel function is also very well known, is widely used in various engineering and science problems, and therefore, we should know what is Bessel function and how to find out the Laplace transform of the Bessel function. The Bessel function we define like this way: the differential equation x square d2y dx square plus x dy dx plus x square minus n square into y equals 0 is known as the Bessel differential equation or Bessel equation of order n. Please note that whenever any equation is coming in this format, x square d2y dx square plus x dy dx plus x square minus n square of y equals 0 is known as Bessel differential equation or Bessel equation of order n. And now, when n is not an integer or 0, the complete solution of Bessel function we write like this: a j n x plus b j minus n x, where j n and j minus n are totally independent. Please note this one. J n and j minus n are independent, and j n x is defined like this way: j n x equals r equals 0 to infinity minus 1 to the power r factorial r gamma n plus r plus 1 into x by 2 to the power n plus 2r, and this we can write down x to the power n 2 to the power n gamma n plus 1 into this series, which we call as Bessel function of first kind of order n. So, j n x equals this series, which is known as the Bessel function of first kind of order n, whereas when n is not an integer and this thing, your j minus n into x is minus 1 to the power n into j n x. Please note that it is beyond our scope in this particular course to tell how we derived j n x, or how I am saying j minus n x equals minus 1 to the power n into j n x, because for that I have to go to some special function theory we have to go through. So, I am skipping that one. Directly I am telling the solution of the differential equation, which we are saying as Bessel differential equation. So, the complete solution we write it as a j n x plus b y n x, where y n x we call it as the Bessel function of second kind of order n, or sometimes we call it as Neumann function also. So, complete solution we write it in the form of y equals a j n x plus b y n x, and y n x is known as the Bessel function of second kind of order n. Now, the solution of Bessel equation for n equals 0. What happens? If I go through this, whenever n is 0, your equation is transformed to d2y dx square plus 1 by x into dy dx plus y equals 0. This equation is known as the Bessel equation for n equals 0. And the solution is, we write it in the form of j0x. This will be equals to 1 minus x square by 2 square plus x to the power 4 into 2 square 4 into 4 square minus x to the power 6 into 2 square into 4 square into 6 square. Like this way it is going on, where j0x is known as the Bessel function of order 0. Please note that j0x is known as Bessel function of order 0. So, basically we are saying that for n equals 0, we are getting this equation, and solution is j0x, where j0x we call it as the Bessel function of order 0. Now see, we want to find out a long example we are taking. First, we will prove that Laplace transform of J0 t is 1 by root s plus 1. From there, we will try to find out Laplace transform of J0 at. Then we will go through the Laplace transform of t J0 at. Also Laplace transform of e power minus at J0 at. And if I integrate the J0 at, that is 0 to infinity J0 at dt. And that is the reason you can understand why I told what is J0x, what is Jnx. So, J0x is called the Bessel function of order 0th order, and Jnx is the Bessel function of order n. So, one by one we want to prove this thing. Let us see this one. The first one is, as I told you, J0 t is nothing but 1 minus t square by 2 square, I have written it, plus t4 by 2 square into 4 square minus t to the power 6 by 2 square 4 square into 6 square, like that way it will continue. So, what will be your Laplace transform of J0 t? Laplace transform of J0 t, this using the linearity property I can write down, this is equals Laplace transform of 1 minus Laplace transform of t square by 2 square plus Laplace transform of t4 by 2 square into 4 square, like this way it will continue. And I know the Laplace transform of each of them. Laplace transform of 1 is 1 by s, 1 by 2 square will go out. So, Laplace transform of 2 square is factorial 2 by s cube, we can do it easily, plus 1 by 2 square into 4 square into t to the power 4 will be factorial 4 by factorial 4 by s to the power 5, and like this way it will again continue. So, that 1 by s if you take common, you will obtain 1 minus half will go out. So, half into 1 by s square plus here factorial 4 is there. So, you will get 1 into 3, and here 2 into 4, 2 and 4 will be cancelled. So, 1 by s has gone out. So, it will be 1 by s square whole square, and like this. And this series is nothing but 1 by s into 1 plus 1 by s square whole to the power minus half, 1 plus x to the power minus half, this we can write down. So, this is a series known to us, it becomes 1 by s into 1 by 1 plus 1 by s square to the power minus half. So, that if I break it, I will obtain 1 by root over 1 plus s square. So, therefore, the Laplace transform of J0 t is nothing but 1 by s square plus 1, and we can evaluate it like this way. So, therefore, if I do not know the Bessel function, it will become very difficult for me to find out the Laplace transform. So, we are finding the general forms. So, even if one who is using Bessel function and Laplace transform, directly they can use this formula and they can find out the solution of their original problems. So, just here we are writing this 1 by this, and ultimately you will obtain 1 by s into this, which is nothing but 1 by s square plus 1. Now, the next one, that is Laplace transform of J0 at, that is number 1. You know this thing, Laplace transform of f of at, this is equals 1 by f of s by a. We know this one, this property f of a, if Laplace transform of f t is f s, then Laplace transform of f of a t is 1 by f of s a. So, we know Laplace transform of J0 t. So, from there directly I can write down Laplace transform of J0 at, that is 1 by a into 1 by root over 1 plus s by a whole square, and if I simplify it, this will become 1 by root over s square plus s square. Therefore, Laplace transform of J0t is root over 1 plus s square, and Laplace transform of J0at, this is equals 1 by root over s square plus s square. So, I think it is clear. Once I know the Laplace transform of J0t, very easily I can find out the Laplace transform of J0at. Number 2, we have to find out the Laplace transform of t into J0at. Laplace transform of t into J0at. This again using the property, I can write it as it is multiplied by t. So, minus dds of Laplace transform of J0at. So, once I have done it, I already know the Laplace transform of J0at, which is nothing but 1 by root over s square plus s square. So, I have to just differentiate this function 1 by s square plus s square once to obtain the required result, and if I do it, I will obtain it as s square plus s square to the power 3 by 2. So, this is the second one, that Laplace transform of t into J0at is equals to s by s square plus s square to the power 3 by 2. Let us go to the number 3, that is Laplace transform of e power minus at into ft. E power, just let me rewrite, Laplace transform of e power minus at into ft. This is equals f of s plus a. If Laplace transform of ft is fs, we know that Laplace transform of e power minus at into ft is f of s plus a. So, that Laplace transform of e power minus at into J0at, this is equals to simply s will be replaced by s plus a in the earlier example. So, that 1 by root over s plus a whole square plus s square, and I will obtain the result as 1 by root over s square plus twice as plus twice s square. So, that I am getting the Laplace transform of e power minus at J0at as 1 by root over s square plus twice as plus twice s square. And number 4 was Laplace transform of J0t. Already we know this is 1 by root over s square plus 1. This we know it. Therefore, what will be the value of J0 to infinity J0t dt? Actually, what is this? This is nothing but, from definition, e power minus st into J0 dt, J0t dt. So, effectively, if you put on this equation s equals 0, then you will obtain 0 to infinity J0 to dt, and this is equals, if I put s equals 0 on this, I will obtain the value as this one. So, what I am getting, 0 to infinity J0t dt, this is equals 1, and this directly by substituting s equals 0, I am obtaining this thing. So, just let us see what happens. Whatever I told, Laplace transform of f at u we have done. Initially there was this thing J0t, Laplace transform, from there number 1 we did, this one Laplace transform of J0at, then Laplace transform of t J0at we are finding out. In the third problem, we are finding the Laplace transform of e power minus at into J0at. Then in fourth, we are finding the Laplace transform of 0 to infinity J0t dt. This is equals 1, directly we have shown from the theorem. Now, next is, we have done the Laplace transform of J0t. Now, we will go with J1t. We have to prove that Laplace transform of J1t is 1 by 1 minus s by root over 1 plus s square, where J1t is a Bessel function of order 1, and once I know the Laplace transform of J1t, from there we can find out the Laplace transform of J0t also, Laplace transform of t j1 t. So, this is known to us j0 dash t equals minus jnt, j1t. We know this thing. How we have proved? The proof is there. We will not discuss that part, but we are assuming that just like we have assumed jnx is the solution, similarly we are assuming j0 dash t equals minus j1t. Now also you know this thing, Laplace transform of f dash t, this is equals s into Laplace transform of ft minus f0, this also we know. So therefore, here Laplace transform of j1t, this is equals minus Laplace transform of j0 dash t. You can write down this, we can write from here minus Laplace transform of j0 t, and so that from here we are writing minus s into Laplace transform of j0 t minus j0 0. So, this is equals minus s into root over 1 plus s square minus 1. j0 0 is 1, already we know. Already we know Laplace transform of j0 t is 1 plus s square, and the value is equals to, then this will be equals to 1 minus s by root over 1 plus s square. So, therefore, Laplace transform of j1t is 1 minus s by root over 1 plus s square. Next, we have to find out the Laplace transform of t j1t. So, Laplace transform of t j1t, again using the property of Laplace transform minus dds of Laplace transform of j1t, and already we evaluated the Laplace transform of j1t. So, minus dds of 1 minus s by minus dds of 1 minus s by root over 1 plus s square. And if we make the dds, I think you will obtain the result as 1 plus s square to the power 3 by 2. Please check the calculation. Please check this calculation, because this may be little bit wrong, although I hope I have done it correctly. So, Laplace transform of t j1t is equals to 1 by 1 plus s square to the power 3 by 2. And so, as I told you, j0 dash t equals minus j1t. From here, I am finding out the Laplace transform of j1t and this one. So, ultimately, Laplace transform of this is 1 minus j1t is this, Laplace transform of t j1t is this one, and minus dds of this, and from there I am finding out 1 by s square plus 32. Fine. So, this is equals to the Laplace transform of j1t, one root over will come, root over is missing. In the second last line, 1 minus s by root over 1 plus s square will be there, the value will be this. Let us see a function which we call as a null function. If nt is a function of t such that for all greater than 0, 0 to t nu du, this is equals to 0. Whenever t greater than 0, 0 to t nu du is 0, then we call nt as a null function. Please note this one. If nt is a function of t such that for all t greater than 0, 0 to t nu du equals 0, then we call nt as a null function. Just for example, if you take a function like this, say at t equals half, it is half, it is minus 1 at t equals 1, it is 0 otherwise. So, if you make the 0 to t ft dt, always the value will be 1 minus 1. Please note this thing. So, that this is a null function. I think it is clear that In this case, always if you take the integral, the value always will be 1 and minus 1, so it will be 0. Consider this function f t equals 1 when t equals 1 and it is 0 otherwise. Will it be a null function? It is 1 at t equals 1 and at only one point it is 1. So, 0 to t means this is the function is defined like this way, f t equals your 0 to t it is coming null function. So, 1 to 1 whenever it will be there the value will be 0. Whereas, if you consider a function f t, this is 1 when it lies between this and it is 0 otherwise. Please see this function f t equals 1 whenever t lies between 1 to 2 and it is 0 for this. So, for t less than 1 what will happen? Whenever t is less than 1, in that case 0 to t fu du the value will be, if it is less than 1 it is 0 function. So, it is 0. Whenever t lies between 1 to 2 that is 0 to t fu du, so basically 1 to t, it is now coming 1 to t fu du is 1. So, 1 into du and your value will become 1 only, t minus 1. And for t greater than 2, 0 to t fu du, this value again whenever 0 to 2 you are telling t is greater than 2. So, in that case the value of the function is 0. So, you see I am getting the value t minus 1 here. Therefore, this function is not a null function. This function is not a null function. Please note this one. Whereas the function which I defined earlier f t equals 1 at t equals 1 and it is 0 otherwise, which I told earlier, this function is this one is a null function, because if you calculate the 0 to t f t dt, in this case the value will be equals to 0. So, null function is a function such that whenever t greater than 0, if you integrate the 0 to t fu du, this will be u, fu du if you consider, then in that case your value will be 0. You may ask why we are going for the null function. Of course, there are certain reasons for studying this null function. It is related to the next topics, that is the inverse Laplace transform. So, as I told you, this function f t equals 1, t equals half, minus 1 at t equals 1 and 0 otherwise is a example of a null function. Another example, as I gave you, f t equals 1 or at t equals 1 and 0 otherwise is a null function. This function is not a null function when t lies between 1 to 2, because for t less than 1, as I shown you earlier, for 1 to 2 the value is t minus 1 and for the other case it is equals to 0. So, therefore, the function is not a null function. And some remarks is there, Laplace transform of a null function is always 0. Laplace transform of a null function will be 0, because if you try to calculate it will become 0. And since the Laplace transform of null function is 0 and if the Laplace transform of f t equals say f s, in that case I can write down Laplace transform of f t plus n t, this is equals to f s. So, please note this one. Since Laplace transform of the null function is always 0 and we have the two functions, just like I am just writing this one, then I will go back to this. I am saying Laplace transform of null function nt is 0 and if I have a function ft whose Laplace transform is fs. So, always from the basic property I can write down Laplace transform of ft plus null function, this is equals fs. What is the meaning of this line? The meaning of this line is you may have two different functions, right? You may have two different functions which have same Laplace transform, which has same Laplace transform. Please note this one, that there may be two different functions which have the same Laplace transform. Just like if you consider a function f1t, this is equals e power minus 3t. You consider another function f2t, which is equals to 0 at t equals 1 and e power minus 3t otherwise, e power minus 3t otherwise. If I take these two functions, if you try to calculate the Laplace transform of these two functions, you will find out that the Laplace transform of both are same. That is, this is equals to 1 by s plus 3 will come, Laplace transform of f1t, and this is equals also Laplace transform of f2t. So, please note this one, I am giving you two different functions, but the Laplace transform of both are same in this case. So, if we allow Laplace transform, then the Laplace transform, the inverse Laplace transform I will tell will not be unique, otherwise it may be unique. So, please note that at present, since I have not considered inverse Laplace transform till now, so let us go to this position that there may have two different functions which has the same Laplace transform. In the next lecture, we will see what is the implication of this thing. Thank you.